So, like I said, we're going to talk about some units today. I want to make sure everybody's on the same page because, like I said before, a lot of you came from different grade schools. So, I want to make sure everybody has all the same starting information. So, since we're in a science class, we will be using the SI units, or this International System of Units. Okay, we're going to talk about some of the advantages of that, but I want to go over what are the SI units. Okay, I want you guys to tell me what these units are, just to start out with, what you know of the units, what things we might want to measure, what units measure them. And then we're going to go back through and talk about something called derived units, okay, and base units, okay, because it's important to know the difference. Cool? All right. So, can you guys think of an SI unit? You probably used it in science class before. Maybe one that might be like on a ruler. Any ideas? Yeah. A meter, okay? So, a meter is definitely an SI unit. Okay, and this is going to be our standard measurement for length or height or anything that you would measure with a ruler or a measuring tape or anything like that. Okay, I know you guys have heard of centimeters, millimeters, kilometers, right? We're going to talk about how prefixes affect the base unit after we go through all the units. Sound good? Okay. So meters is your unit for length. Also, it doesn't look like the camera is focusing very well. Looks a little better. Oh, that was the light. All right, that's much better. All right. Other units you guys can think of. Yeah. Liters, right? Liters is a good one. Okay, so what does liter measure? Ready? When you buy a 2 liter of soda, what does it tell you about the soda you're buying? It tells you the volume. Okay, it's actually a great one to do second because liter is a derived unit. Okay, liter can be stated in other units. Okay, that's the definition of a derived unit. Okay, so a liter is 1 decimeter cubed. Okay, so a decimeter is 1/10 of a meter. So if we look at the meter stick and we go from like 10 to 20, okay, that's 10 centimeters. Okay, so if we made a cube that had side lengths of 10 centimeters, like this, we made a cube out of this, we would get the volume of that cube would be 1 liter. Does that kind of make sense? Okay, so our derived units are going to be units that we can write a different way. So this is 1 decimeter. One decimeter cubed, we could write this as 1 dm. Okay, decimeter is a not super common unit. Okay, we could write it as 1/10 of a meter cubed. So 0.1 meters cubed. We could write it that way too. Good? Any questions? No? Okay. Alrighty. So we've got our volume. What else? Okay. Maybe an easier question. What are some things that you might want to measure in science? So we've got volume, we've got length. Yeah. Width? We're going to use meters for width as well. Yeah? Mass. Mass is a great one. What's our unit for mass? Any ideas? Yeah. That is partially almost correct. If it was not the weird one, you would be correct. Okay? So mass is kind of weird. Okay. So the reason why it's kind of weird is they decided to set the value for a gram as about the same weight as a paper clip. Okay? So paper clips are not very big, right? So if we try and measure the weight of even like an elephant in paper clips, is that going to be super convenient? No, there's going to be a lot of zeros there. Okay? Now if we try and measure something like a planet in paper clips, you're going to want to use scientific notation, right? Because that's a lot of zeros. Okay? So because there's so many zeros, it ends up not being practical for having grams as our base unit. Okay? So this is going to be the one weird base unit that we have. And instead of it being grams, it's going to be kilograms, because taking 1,000 grams is a much more reasonable unit for us to use in everyday life. Cool? Okay. The ones that I'm putting stars by are your base units. Alrighty. What other quantities might you want to measure? Yeah. Density. Okay. Density is going to be a derived unit. There's not so much a specific unit for it, right? So density is your mass divided by your volume, right? Yeah. So we're going to have generally kilograms per liter or kilograms per some form of cubic meter. That's probably going to be a little bit more common. As far as I know, there's not just a unit for density. It's just something per like cubic meter. Okay, so we're not going to write that one down. That is an important quantity though. All right, other ones. What things have you measured in science labs before or talked about? Yeah. Weight. Weight is going to be a good one. Weight's going to be another derived unit. I'm going to be really impressed if somebody has heard of the SI unit for weight. Any guesses? You don't really normally use this one unless you are specifically in science. It's named after a famous scientist. Anybody want to guess? Yeah.
Vector or something?
No, we're going to get to vectors later, though. Vectors are a different thing. Any other guesses? Yeah? It is a Newton, right? Actually. So one thing I want to mention, I accidentally capitalized kilograms. It should not have been capitalized, but newtons will be. Okay? So a Newton is a measure of force or weight. This is not a base unit. It is a derived unit. Okay, so force or weight is a Newton. Okay? Newtons are going to be a little bit more complicated than our just volume, our liter that we have up here. Okay? So this is going to be a time where I'm going to explain a little bit more with our derived units. Okay? First, physicists tend to be a little bit on the lazy side. Okay? And if they find a cluster of units that has some meaning, so in this case, it always showed up when they were talking about force or weight, they are going to redefine that and give it a different name. Okay? So for newtons, that group of units that they found always popping up was kilograms times meters over seconds squared. Okay, so we have our mass times a distance divided by a unit of time squared. Okay, and we find that that's pretty much always what pops up. Actually, it is always what pops up anytime we're talking about force. And so instead of just kind of keeping that group of units there, we replace it with newtons, because it not only makes it less for us to write, it also makes it a little bit easier to see, hey, this quantity is force. Does that make sense? Yeah, no, maybe? Okay. All right, so this is kind of what our derived units are going to look like. You'll have a unit, and then you'll have what it's made out of. Good? Okay. All right, so we got force, we've got weight. We just added one up there that we haven't added on our list. What quantity did we put up there? We have that on our list, okay? So we've got kilograms times meters over seconds squared. Is seconds on the board? No, okay? So our SI unit for time is going to be actually seconds, okay? Even when you are talking about some stuff that's fairly long, unless you're getting to things that are like lengths of things that happen in the universe, you are actually going to use seconds. It just kind of makes it a little bit more standard across the board, okay? Okay, and seconds is a base unit. Forgot to stop. All right, other things. Why do we have the air conditioner on? What are we changing? Okay, the temperature. So we should probably measure temperature in science, right? Seems pretty important. What units do you think we'll use for temperature? Okay, degrees Celsius is an excellent guess. That is very, very close to correct, but it is not the technical SI unit for temperature. Okay? It's really close because it's actually just a little bit shifted. It's the same size degree. Anybody know what the other scale might be? No? There will be times where we will use Celsius in here, just because most thermometers measure that more directly, more commonly. Anybody? It is named after another scientist. It is probably not one that you've heard of commonly. No, nobody's heard of it? All right, so the official SI unit for temperature is Kelvin, okay? It is named after a scientist, like I said. So we're going to capitalize this one too. All right. Now, with Celsius, we know the 0 point of Celsius is when water freezes, right? You guys know that, right? Okay. So, if our 0 point is where water freezes, we're going to get negative temperatures all the time, right? Because outside, it could be negative Celsius pretty easily in winter, right? Yeah. So, part of the reason why the actual official unit for temperature in the SI unit is Kelvin is because the 0 point of Kelvin is actually absolute zero. That means that in any ordinary circumstance where we're going to be using temperature, we're not going to have to deal with negatives, okay? I don't know about you, but I prefer not to deal with negatives if I can, right? Negatives kind of get a little bit annoying sometimes. So, that's why they use Kelvin instead of Celsius, okay? The only difference between Kelvin and Celsius is that 0 point. The degree size is exactly the same, so converting from Kelvin to Celsius is really easy. All you do is you either add or subtract 273. That's all you have to do, okay? So if you start in Celsius, you're going to add 273 to move that 0 point down to 0, okay? So Kelvin should always be a bigger number than Celsius. If you start in Kelvin, you're going to subtract 273. Make sense? And we'll go over converting and stuff like that later. But I just want to kind of make sure you guys are aware of that. Because you guys have probably seen the formula for converting Fahrenheit to Celsius, right? Yeah, that's one of the most complicated conversions. Kelvin to Celsius is ridiculously easy. Cool? All right. Any questions? No? All righty, let's see here. All right, most of the ones that we don't have up here, I don't know if you're going to guess. So, do you want me to just tell you what they are? Okay. All right. Does everybody have these written down? Because I think I'm going to have to start erasing stuff. I don't want to erase our units, so I'm going to erase these derived units and what they're equal to, so that we have more room over here. Alrighty. So we've got the meter, we've got the kilogram, seconds, Kelvin, we've got liters, and we've got newtons. Okay. One that I do want to talk about so that you kind of are aware of it once we get to light and sound is this idea of frequency. Okay, so it measures how fast something repeats. And this is going to be something that we use a lot with light and sound because both of them are wave-like vibrations. Okay, you've probably heard this before, especially if you have a speaker system or something like that. They're generally rated by this value, and this value is hertz. Okay. So hertz is a measure of frequency. Okay? Frequency is not a base unit. Like I said, it's a measure of how frequently something happens. So its measurement in base units is 1 over seconds. Okay? So that 1 kind of represents whatever you're counting. So it's how many of those things occur or pass you or whatever per second. Make sense? Yeah. Yes, it is named after a scientist. Okay, so we've got hertz. The next one is going to be our measure of energy. Okay, when I say it, keep in mind it is spelled differently than the thing that sounds like it. Got it? Okay. So our unit for energy, so the SI unit for energy is named after a French scientist whose last name was Joule. Okay. Okay. It is spelled Joule. Okay. Like I said, it's the French guy's last name. It's going to be spelled weird, at least for us. So joules is another derived unit. It's kind of, we're stepping up a little bit in complication here. Okay. So joules, like I said, is a unit of energy. It's going to be, I guess I should write that down. It's going to be a little more complicated, and we're going to have multiple different ways we can write this because it is a little more complicated. Okay. So for joules, we can write it as newtons times meters. Okay, so force times distance. Okay, when we get to work, that will be very, very familiar. Okay, so force times distance. Okay, I guess I could add work on. Now, when we look at this, we can say, hey, newtons is a derived unit. Okay, I know I erased what it was equal to, but we can write this down. So kilograms times meters over seconds squared is newtons times meters from here. Okay. So our final breakdown of joules is going to be kilograms meters squared over seconds squared. Okay. So like I said, it's a little bit more complicated, but when we compare it to our newtons, really all we did was add a factor of meters. Does that kind of make sense? Okay. All right, so we've got energy, we've got force. I do also want to talk about power. Okay, so power is how much energy you're using per second. Okay, so our unit for power is watt. You've probably heard of watts before when we're talking about like electricity or rating for light bulbs even. So watt is going to be our measure of power. I need to switch back to the other green marker. The other green marker was working better. Okay, so we've got power. Watt is energy per second. So it should not be surprising that if we break this down into its parts, we will get joules, which is our unit of energy, per second. Okay, so it's energy per second. We can also write this equal signs. Newtons times meters over seconds. Okay. So all we did was replace joules with newtons per meter. Right? Okay. Or we could simplify this even farther down to our actual base units. Okay, so we're going to put kilograms times meters over seconds squared in for newtons times meters. Okay, I'm going to write it like that so you guys hopefully haven't forgotten how to multiply fractions, but this should make it a little bit easier. Okay, so we're going to multiply our numerators and multiply our denominators. So we end up with kilograms meters squared over seconds. Kind of makes sense? Okay. Now, part of the reason why I have written them out, especially watts, in so many different forms is because I want you guys to be really, really careful about your units this year. And so if you're looking at a problem and maybe you started your problem with a force or something like that, so then your units would show up in newtons times meters over seconds, okay? And in that case, you would be able to look at this and say, hey, that's joules, or watts, sorry, not joules. Or maybe you started with energy per second and we're just seriously just calculating your power of energy per second. Then you would have this, which would tell you watts, okay? Or maybe you started with everything in base units, okay? That's when you're going to end up with this, okay? And I want you to be able to identify whether that thing is energy or force or length or anything like that. Does that make sense? Okay. So I know you guys, at least a lot of freshmen come in thinking that writing units is silly and pointless and not helpful. It really actually is very, very, very helpful. It's actually a great way to check your work, okay? So we know what even these clusters of units are equal to, or we know what our base units are used for, okay? So if you're doing a calculation and you should be finding the mass of a bouncy ball or something like that, you hope that your answer has units of kilograms, right? Yeah. If it doesn't have units of kilograms, that's actually a really good indication that you've done it wrong. If it does have kilograms, it's a really good indication that you've done it right. Okay? So that's a really, really, really fast and efficient way to check whether you have actually done the problem correctly. And you really don't have to do any work or extra work. You just have to make sure you keep track of your units. Does that make sense? Okay. The other reason why we want to use these units, we're doing science. We're talking about things that are real, physical things. Okay. We need to know what those physical things are. Okay. So if I wrote up on the board 2, there's 2 of something, but you wouldn't know how to use that, right? You wouldn't know if it's 2 meters. So maybe you're supposed to walk 2 meters, or maybe it's 2 kilograms. Maybe you're supposed to pick up 2 kilogram weights and do something. You wouldn't know if it's 2 joules of energy, right? You wouldn't know what that number is unless you have your units, okay? I can tell you right now, 2 joules of energy and 2 meters are 2 very, very different things. Cool? Any questions? No? All right. So we've talked about our derived units. We've talked about our base units. And we have a list of pretty much every unit we are going to use this year. We might talk about a few other ones. Normally, we do not have time to get to electricity. We are going faster this year than normal, so there's a small chance we might. If we do, then I'll go over those. If you're interested, we're going to have things like amps for electrical current, volts for the power behind the flow of electricity, and ohms, which is something called resistance. So it's resistance to the flow of electricity in a wire. Those are all very important things for a circuit. We might actually in one class already, we've talked about moles sort of as a sidetrack. Not the furry animal that digs in the ground, but a measure of the number of atoms. Okay, so a mole is actually a very useful number of atoms. You will talk about it a ton in chemistry, but it ends up being the number of atoms in essentially. So if you take any of these elements, they all have an atomic mass, right? Yeah. If you take a mole of those atoms, you will have the number that the atomic mass is in grams of that substance. Okay. So if we look at, let's say, boron. Okay. So if we had a mole of boron, it would be 10.81 grams. Okay, so that's a really good way to know approximately how many atoms you have. Cool? All right, so moles are very useful. You will use those a lot in chemistry. We probably won't use them a whole ton in here. There's a few other ones. An old unit for luminous intensity that's listed in your book is candela. Okay. What it does is it essentially measures how much light a light bulb is putting out based on how many candles it would take to put out that same amount of light. Does that kind of make sense? Okay, so it's an old unit. It is not a more recent unit that we would use commonly. We now use one called lux much more frequently, and there's a few others. When you're looking at luminous intensity, there's a few different measurements and how you can measure that. So a lot of them actually, instead of measuring the brightness of the light itself, measure essentially like, we'll look right here on my desk. How bright is it right here on my desk? Okay, that answer is going to be different than if I go like on my chair when it's pushed into the desk, right? Under the desk, it's going to be a lot darker than on top of my desk, right? That measurement tends to be a lot more useful depending on what you're doing, because if you are, say, I know I deal with this a little bit more because I deal with fish tanks, but if you're trying to make sure that plants at the bottom of a fish tank are getting a proper amount of light, it's not near as important how much light your actual light bulb's putting out as to how much light makes it to the plants at the bottom of the tank, right? Okay. So there you're actually dealing with some calculations with how deep the tank is and things like that. So there's some other factors that play into that. Cool? Okay. Yeah. The only other one that we might possibly use is Pascal's. Have you guys heard of Pascal's before? You've probably heard of it if you've watched Tangled. It's the name of the chameleon. Let's see here. I lost my marker. I'm already starting to lose my markers. It's the beginning of the year. Alrighty. So, Pascal, I will write down on the off chance we do make it there. It is a unit of pressure. Okay? We'll put it. Okay, so Pascal's is a unit of pressure. Pressure is going to be our force per unit area. Okay, so what do we use to measure area? Any ideas? Yeah. Length times width. Okay, so our units are going to end up being meters squared. Does that make sense? Yeah. So we've got meters squared. So if we have force per unit area, what do you think would be on top? What's our unit for force? Newtons. Okay, so pressure is going to be newtons per meter squared. This will end up canceling out a meter. So we end up with kilograms, meters, over seconds. Or meters times seconds. That I've not. Okay. There we go. Now it's right. Kilograms divided by meters times seconds. Does that kind of make sense? Any questions on any of these units or any other units you've heard of? There are some pretty weird ones out there. Yeah. There's some pretty good ones. One of my favorites is the slug, which is a unit of mass. It's an Old English unit of mass. That goes with like leagues and other values like that. The English, so people in Britain still use a few measurements of mass that we don't, or actually I guess it's technically weight. So they still use stones sometimes. To hear some British YouTubers and stuff say like this was like, or I weigh like 9 stone or something like that. That's a measurement of weight. Stones, I think, are about 14 pounds. Cool? Okay. Those are not SI units, but they're just fun units to talk about. Any questions? No? All right. So the next thing I want to talk about is all of these units can be used with the prefixes. Okay? You guys have heard of some of the prefixes before. Okay? So when we talk about meters, right, you've heard of centimeters. Okay? We can look at this ruler and we can see, okay, we've got the whole thing is a meter, right? This is a meter stick. Then we look at these markings where we've got numbers here. Those are centimeters, okay? Okay? There's 100 centimeters in a meter. You probably already know that, right? Okay? Now, if we took a gram, okay, and then we had a centigram, how many centigrams would be in a gram? 100, okay? Now, if we took, let's say, a liter, and then we had centiliters. How many centiliters would be in a liter? 100. Okay? So these prefixes mean the same thing no matter what unit you put them in front of. Does that make sense? So if we have centi, you're dividing that base, whatever you have behind it, into 100 parts. Okay? Does that make sense? All right. Can I erase the units and then put the prefixes up here? Okay. Okay, so our SI unit prefixes. The ones that I want you to know, okay, we're going to start with small ones, okay? Your book lists a few that really aren't used very commonly. So things like femto, okay? Femto is really ridiculously tiny, okay? Most of the time, if you're using femtometers or something like that, you're literally measuring the size of atoms. Molecules generally are in nanometers. Okay, so femtometers is like literally the size of atoms. Nanometers, once we get to light, we will use nanometers a lot more frequently. But I don't think I need you to know the nano prefix. Okay. The next one, though, is micro. Still debating if I want you to know micro. Let's go with no, because we probably won't use it in this class. We'll probably use nano more frequently than micro. I do want to make a note on micro, just because you might see this listed somewhere. The prefix for micro is actually a Greek letter, okay? So if you see something written like this, that's not just a fancy U. That is the Greek letter mu, okay? So this would be micrometers. Cool. So that's the prefix for that abbreviation. So that's micro. The ones that I do definitely want you to know are the ones that you're probably the most familiar with, okay? So the first prefix that I definitely want you to know, we're going to start from smallest and go to biggest, is milli. Okay? So anytime you put that milli prefix in front of any unit, you're going to divide it into 1,000 pieces. Okay? So it's going to be okay, so it's going to be 0.001 of whatever it is that you're talking about. Okay? So this is also equal to 1 over 1,000, if you like that better. Okay, so 1/1000. If you want to write this in scientific notation, which sometimes is easier, it's going to be 10 to the negative third. Okay? Just a refresher, negative powers of 10, move your decimal place this way. Good? Okay. When we are doing conversions and things like this, it's always good to remember that 1 millimeter or 1 milliliter, milligram, anything like that is going to be smaller than your base unit. Okay? So if you're converting to from 1 gram to milligrams, you should get a big number because you're going to need more milligrams or millimeters to make up that meter. Does that make sense? Okay. All right, so it's 1/1000. Okay. The next one is centi. We already kind of talked about this. This is going to be 100th. Okay, so 100th or 1 over 100 or 10 to the negative second. Okay, it's probably one that you're very familiar with. The next one, so there is one for 1/10. Okay, we already talked about it a little bit, a decimeter, right? That was our measure of a liter. I'm not going to write that one down because I don't need you to memorize that one, but you should know that it exists. Okay? All right. Now we're going to get to ones that are bigger. So there are like prefixes that go between like your base unit and kilo, but they're not hardly ever used. Okay? Especially for things like meters, right? Decameter would be 10 meters, right? But writing 10 meters is not hard. And most people are going to be more familiar with the quantity of 10 meters than 1 decameter. So we just generally stick to using the base unit until we get to 1,000 of them. Cool? So anybody guess what 1,000 is? Probably the next most common used one. If we have something similar to a mile that we're measuring in SI units, what are we going to call it? If you run a 5K, what are you measuring your distance in? Nope. Kilometers. Okay? So kilo is going to be our next prefix. Okay? So this is where we go from smaller to bigger. So kilo, not doing well with making my lowercase k's look like a lowercase k. Kilo is going to be 1,000 of something. Okay, since it's not a decimal, we're not going to have a fraction. And this is 10 to the positive third. Okay, so milli is 1/1000. Kilo is 1,000 of these things. Okay, so 1 kilometer is 1,000 meters. Good? Okay. That is going to be by far one of the most commonly used ones, right? Especially because it's in front of kilograms, which is one of our base units. So a kilogram is 1,000 grams. Good? All right. The next ones you are going to use most commonly with units of like phone memory or computer memory. Okay? Just because our unit for memory is so small, especially with the way things have gone. So are you guys vaguely familiar with the unit of byte? Yeah? Okay. No unit of memory that we would use today would be measured in single bytes. The smallest files that we have are measured in kilobytes. Okay. So just your standard like Google Doc or something like that where it is nothing but text still is kilobytes. So it's thousands of bytes. All right, we'll do mega, giga, and tera tomorrow. Have a good day, guys.